Please, good day, everyone. So let's now have Module 6. So the first part of Module 6. So this is all about the Kirchhoff's law. Okay, so this Kirchhoff's law, actually, if you were able to understand the module on Ohm's law, then you already have a background for today's session. Okay, so Kirchhoff's law, Kirchhoff's voltage law states that the voltage applied to a closed circuit equals the sum of the voltage drops in that circuit. So what do we mean by this? Kirchhoff's voltage law states that the voltage applied to a closed circuit equals the sum of the voltage drops in that circuit. So what do we mean by this is the voltage applied to a closed circuit will be equal now, should equal to the every drop of voltage, to the sum of every drop of voltage in a particular circuit. Okay, so voltage, you will see here, voltage applied equals sum of voltage drops. So VA here stands for voltage applied. Then this V sub 1, V sub 2, V sub 3, it's not always until 3, it depends on the circuit. This is just an example. This 1, 2, 3, these are the voltage drops. Okay. So where VA is the applied voltage and V1, V2, V3 are the voltage drops. Another way of stating Kirchhoff's voltage law is that the algebraic sum of the voltage rises and voltage drops must be equal to 0. So what do we mean by this? So if you're going to illustrate this now as a formula, this statement, how are you going to show this? I want to ask, what am I going to ask? I'm going to ask now Jojo Agustino. How are you going now to show this statement? Like just like for example, this one, voltage. Like for this one, voltage applied to closed circuit equals the sum of the voltage drops in the circuit. So just like here, voltage applied is equal to the sum of the voltage drops. For example, this, okay, so this is an example. So now, for Jojo, this question is for Jojo Dimakiling and for Yin, Jojo Agostino and for Yin Amador, also Rickling Balbin. Can you please write the formula for this statement? Another way of stating KVL is that the algebraic sum of the voltage rises and voltage drops must be equal to 0. So you just have to make a formula for this statement. Okay? So an example for what I'm asking you is like this. Voltage applied is equal to the sum equal to the sum of the voltage drops. Okay, so how are you going to answer now, Jojo, Corinne, Brickelin? Is you just have to write through a formula to describe this statement. Okay, So how are you going to show me your answer? You just have to write in the YouTube comment section your answer, but first write the question before you answer. Okay, so a voltage source or EMF is considered a voltage rise. A voltage across a resistor is a voltage drop. Often for convenience in labeling, letter subscripts are shown for voltage sources and numerical subscripts for voltage drops. This form of the law can be written, but transposing the right members of the equation shown above to the left side. So let's see. Okay, so just like this. Okay, so let's have this one. Using a new symbol, this symbol is a Greek capital letter sigma. We have the summation of the voltages is equal to voltage applied minus the voltage drops. These are the voltage drops equals 0, in which the summation of V sub 1, the algebraic sum of all the voltages around a closed circuit, equals 0. So this sigma means sum of. Okay, so we assign a plus a plus positive sign to a voltage rise and a negative sign to the voltage drop. Okay, the voltage applied is the total voltage. The numbers here, again, these are the voltage drops. These are the voltage drops. So in tracing voltage drops around the circuit, start at the negative terminal of the voltage source. The path from the negative terminal to the positive terminal to the source is a voltage rise. Take note, the path from the negative terminal to the positive terminal to the source is a voltage rise. So we continue to trace the circuit from the positive terminal through all the resistors and back to the negative terminal of the source. In the equation given a while ago, if we start at a point A, the negative terminal of the battery, and move around the circuit in the direction A, B, C, D, we go through the VA from negative to positive, and V applied, the voltage applied is equal to positive 100. So where is this? This one. So the terminal that we're referring now a while ago is this, negative, positive. Okay, so it is said that the path from negative terminal to the positive terminal through the source is the voltage applied. Okay, so here, so where are we now? So, and move around the circuit in direction A, B, C, D. So where's the A, B, C, D? A, B, C, D. This is the circuit A, B, C, D. Okay, so we go through voltage applied from the voltage applied from the negative terminal to positive terminal. Positive terminal. And voltage applied, therefore, is equals to positive 100 volts. So if we start at point B, and move in the opposite direction, AEDCB, we start at this direction and move to B. A while ago, the movement was A. The example is A, B, C, D. This time, if we start at point B and move in the opposite direction, if we do the opposite direction instead of A, B, C, D, if we use point B as the starting point, B, A, D, C, C, B. VA from positive to negative. So from positive to negative. So therefore, the voltage applied will be what? Joshua Bantayan and Syra Jean Bedeo. So the example that I mentioned a while ago is if we move, if the circuit move this way from starting from the point A, B, C, D, since it passes now the terminal negative to positive. So if the direction is like that, like this, A, B, C, D, so therefore the voltage applied is positive. The question now is, how about if our starting point is B and we will be doing the opposite direction, B, A, D, C, B. So what will be now the sign for the voltage applied? Again, for Joshua and Saya. Okay, so the voltage, so now that's in figure 1, if we trace the circuit in the direction AB, going back to ABCD, voltage 1 is equal to negative 50 voltage. Why negative 50? Why this voltage 1? If we move now if we will be using the previous direction, moving from A, B, C, D, in which the voltage applied is positive 100 volts. So the question now is why it's negative, why the V1 now, the first voltage drop now is negative 50. So why it's negative 50 now? Okay. Jeans Shervo, what is your idea? How about Lovila Rosell? What is your idea? Why the first voltage drop will become negative 50? Okay, and so on. Same with V2 and V3. Okay. Okay, so in example 1, determine the direction of the voltage around the circuit. A, B, C, D. A, that's the figure that is in figure 2. Okay, so this is figure 2. Okay, so this is figure 2. Determine the direction of the voltage around the circuit A, B, C, D, and then write the expression for voltages around the circuit. So let us now take a look. Okay, so this is A, B, C, D. Okay, so VA is the voltage source. It is a voltage rises in the current direction assumed. So where is this VA? Here it is, this VA. This is the VA. V1 is a voltage drop. It is a decrease in the direction assumed. So where's V1? So here is V1. So here is V2. And then the V3. And here's the V3. Alright, so VB is a voltage source. It is a decrease in voltage in the current direction assumed. So VB is negative because the direction is A, B, C, D. Okay, so V3 is a voltage drop. So V is equal to 0. Positive VA, therefore is minus V1 minus V2 minus VB minus V3 is equal to 0. So group the voltage rises and the voltage drops. So VA minus B minus the summation of all the voltage drops. Okay, so notice that the voltage drops include a voltage source VB. Ordinarily, a source would be positive. In this case, the polarity of the source is acting the assumed direction of the current. Therefore, its effect is to decrease the voltage. So again, why its effect is to decrease the voltage of the VB? Manuel Lim and Maria Novella. Can you please answer the question? Why again the effect of the VB is to decrease the voltage? To decrease the voltage. So as shown here in the diagram, I mean in the chart, in the figure. So this is the VB. So this one is the VB. Okay, so for example 2, determine now the voltage of the VB. So let us now solve what is the VB. So the direction of the current flow is shown by the arrow. Okay, so this is the arrow. So it's A, B, C, D. So you're going to mark the polarity of the voltage drops across the resistors, place the circuit in the direction of current flow starting at point A. So this is point A, so it's going there. So let's just follow the direction of the arrow. So write the voltage equation around the circuit. So VA, voltage applied, minus voltage drop 1, minus voltage drop 2, minus voltage B, drop B, minus voltage drop 3 should always be equal to 0. So these are the given now. So how are we now going to determine voltage VB with the given numbers? Voltage applied is equal to 15 volts. And we have voltage drop 1, 3 volts. Voltage drop 2 is 6 volts. Voltage drop 3 is 2 volts. And we are looking for VB. So again, take note that the voltage applied minus the total number, the sum of the voltage drops is equal, should always be equal to 0. Okay. So how are we going to do this? So solve for the VB. Okay. So VB is equal to, again, voltage applied. So it will now be, since voltage applied is equal to the sum of the voltage drops equals 0. So therefore, how are we going to get now the number for VB? So we just have to do it like this. Voltage applied minus V1 minus V2 minus V3 is equal to 15. So 15 equals to, just substitute the value of the given. So it's 4 volts. So how are we going to check now if 4 volts is correct? Can you tell me? Romel, Arlan, June, July, and Alvin Inaro. So this question is for Romel, Arlan, June, and Alvin. So please show me how to recheck if 4 volts is the correct answer for VB. Okay, so let's now have, so we're done with, so I think this is just Kirchhoff's voltage law. It's just a piece of game, just like what I've said a while ago, that if you were able to understand the module on Ohm's law, then it will not be difficult for you to understand the KVL. Okay, so let's have the Kirchhoff's current law. So this time is the current. So Kirchhoff's current law states that the sum of the currents entering a junction is equal to the sum of the currents leaving the junction. Okay, again, Kirchhoff's current law states that the sum of the currents entering a junction is equal to the sum of the currents leaving the junction. So please do not be confused. In Kirchhoff's voltage law, it's the voltage applied is equal to the sum of the voltage, is equal to the sum of the voltage, to the sum of the different voltage drops. So in KCL, the sum of the currents entering a junction. So this is the junction. This is the junction. So the sum of the currents entering this junction is equal to the sum at the currents leaving the junction. So suppose we have 6 currents leaving and entering a common junction or point shown here in this figure. So in this here, this common point is also called a node. So this common point is called junction or node. By the way, question. Let me give you a task. A task for Abigail, Ronald, Sopronio, and Manuel. Okay, can you show me the formula or how to describe this statement? Okay, so just like in KVL, it's like voltage applied is equal to some sigma, the sigma symbol, the voltage drops is equal to the sum of the volume. So here, I want you to those who were called, who are they again? Abigail, Ronald, and Sophronia. Can you show me the formula for this, or how will you illustrate this to a formula? So by just seeing that formula, then we will know, your classmates will know of this statement, will be reminded of this statement. Sum of the currents entering a junction is equal to the sum of the currents leaving the junction. Okay, so again, how do we call this point? This is the node. This common point is called the junction or the node. Okay, so substitute. Okay. So if we consider that the currents flowing toward the junction are positive, flowing toward the junction, so meaning entering the junction is positive, and those currents flowing away the junction are negative, then this law also states that the algebraic sum of all the currents meeting at a common point is 0. Using the symbol sigma again, or the sum, we have here the sum of the currents is equal to 0. Okay, so let's have example 3. So write the equation for current 1. This is the current 1. This is the junction. So again, all the currents entering the junction is equal to the sum of the currents going out from the junction. So for letter A, it's positive I1 minus I2 minus I3 equals 0. Question. Why it's -1 minus I2 minus I3? Okay, Eric. Okay, so here it will become I1, therefore will be I2 plus I3. Okay, so transposition B, figure 5B. So it's like this. So positive I1 minus I2 minus I3 minus I4. So why is it that it's minus I2, I3 minus I4? Question goes to John John. Okay, John John. What is your answer? Why? Again, the question for John John and Eric. Why I1 in A and B is positive, whereas I2, I3 is negative, also here in letter B. Okay. So example 4, let's have example 4. Find the unknown currents in part A and part B in figure 6. So find the unknown current. So the unknown current in letter A is I1. So how are we going now to compute for I1? So it's negative 1, negative I1 plus I2 minus I3. Okay. I want to ask now, J Marvin, why I1 is negative here, also I3, and why I2 is positive, whereas I3 is negative. Okay, to solve this now, it's I1 because of transposition, so I2 minus I3. So it's 7 minus 3 equals to 4 amperes. So letter B. So this is the junction, the node, or the common point. I1, positive I1, I2, I2, okay, positive I2, then I3, plus I4. Okay. Question to Angelina. Angelina. Question, why I1 is positive and I2 including I4, whereas for I3 it's negative sign. So same with what we did in letter A, transposition. So I4, so actually it's, let's see first, okay, for a while. For a while. Okay, for a while class, I'm just going to check on something. Okay, while I'm checking for the answer, please try to reflect on the given slide. So I4 I4 is, so I4 now, negative, this is negative. Negative because of transition. So you will see here it's negative. So negative 2 minus 3. So it's negative 2 minus 3. So it's negative 5. Again, negative 2 minus 3 is negative 5. So add 4, so it's negative 1. So the negative sign for I4 means that the assumed direction of I4, if I4 is incorrect, and that I4 is actually flowing away from point B. Okay. So here, so since it's negative 1, so this means that the assumed direction of I4 is incorrect. So it should be going out from the node or from the junction because we arrive at negative 1. All right. So let's just have the second part to next meeting. So try to reflect first. Those who were not called, so please comment your name. To those who were also not called, you just have to put there who were not called, so that next time you'll be the one to be called. So I hope that you've learned something about the Kirchhoff's voltage law, the KVL, and then the KCL.